Good afternoon, everyone, or good morning, wherever you are in your part of the world. My name is Frank Niese, and it's my pleasure to kick off this virtual winter school workshop on ORCA. And I will just basically do the groundwork so that you can enjoy the more concrete material that you will see later. Um, Okay, let's get started. So the very first thing that I want to do is to tell you who is bringing ORCA to you. And of course, ORCA is a big effort, and it's now well of age. So that's around 25, almost 30 years old. And many people have worked on it. I think the main teams that work on it are the team at the Max Planck Institute for Kohlenforschung here in Mülheim an der Ruhr in Germany, and the team at Facts in Cologne, who is the commercial part of ORCA, who's selling ORCA to industry, but also takes a very active part in the development. And many of the things that you will see in my talk and also in the other talks and the practicals were actually provided by by Facts. And of course, the team at Facts is headed by Christoph Ripplinger, and Christoph and I, we go back very long time. I think Christoph was my first or one of the first PhD students, and we have always enjoyed working together. Now, so I thought it was appropriate that like the first few minutes, I just talk about where ORCA came from. And of course, somebody can ask me later why ORCA is called ORCA, and then I will tell you that I wish I had a better answer than I have. But let's keep that for later. So how did we get to ORCA? And so ORCA started when I was a PhD student in biochemistry at the University of Constance, and we were studying enzymes, metalloenzymes actually. And so there were two enzymes, cytochrome C oxidase, which is a very important enzyme for respiration, and a bacterial enzyme called nitrous oxide reductase. And these two enzymes, they shared one feature, one EPR spectrum um, that was known to be attributable to copper. And at that time, my PhD advisor asked me, what's the structure of that copper site? And of course, I said, I didn't know. And it became clear to me that the only answer can be is to go via quantum mechanics. So I started to learn quantum mechanics and wrote the very first baby version of ORCA, which was at the time written in Turbo Pascal and was using semi-empirical theory. But it had the very clear and intended purpose to be able to calculate spectra. And at that time, like an ab initio calculation on benzene was an adventure, and there was almost nothing available to calculate open shell transition metal complex, and that is why I resorted to semi-empirical theory. And that happened to be a very successful endeavor. So what you see on this slide, I think were the first MCD spectra that were calculated by quantum mechanics, and um, they matched the experiment very well. And so what we found out in that at that time was that that copper side that gave rise to the strange signal is actually a copper dimer with one unpaired electron that is delocalized over two copper centers. So it's a delocalized mixed valence di-copper center, and it happened to also be the first metal-metal bond in biology. So that was exciting times, and then went on to do a postdoc in the US at Stanford University, and like my lab mates started to use the program, and so we were having a lot of fun. I really enjoyed doing that, and it was growing and adding more features and more spectroscopic properties. But that was in the late 90s, and semi-empirical quantum chemistry very much fell out of fashion. And so you started, despite the fact that it was working very well, started to get comments from referees telling us that that's not state of the art, and what you really should do is DFT, and like that's not cutting it, etc., etc. And so, all right, so we were having fun with semi-empirical quantum chemistry, but the referees stopped having fun, no matter how good the results were or like how well you could model the experiment. They didn't want it. And so that was then the point in time where I decided, okay, it has to start again. And it has to be density functional theory. And at that point, I went back to Germany and started my habilitation. And in the first few months of my habilitation, I rewrote what I had written in Turbo Pascal and C++, and also started adding DFT and all of these things. So actually, the very first module that was written was the ORCA MRCI program. And so that is all in my habilitation thesis. That is very massive, almost textbook on quantum chemistry and integrals and all of these things. And so that code, to a large extent, still exists today and is like everybody hates it, but like it's still at the core of what ORCA is now. The idea was always to create a program that would facilitate the connection between theory and experiment, because in my heart, I'm a spectroscopist. I'm not a theoretician, but in my heart, I'm a spectroscopist doing theory. And so I always wanted to have a program that helps me connecting theory and experiment. And usually, in my opinion, and that's still my opinion after a few decades, the best way to do that is to go via spectroscopy. But then, of course, the program should be flexible and efficient and comprehensive and user-friendly and easily extendable and well-structured. And of course, well-structured, that is a moving target as you start working on it with dozens of people. It becomes more and more of a problem. And of course, it should be platform independent, and that means we're not making use of anything that's operating specific, and we're also not making use of external libraries until we absolutely have to. And that has served us very, very well over. All right, so I try to speed up a bit so that we can get to the end. All right, so that was then around 2000, and then up to 2005, various modules were developed, including the TDDFT and the CPSCF and all of that. And then I started to have my own students, and one of the very first was Frank Venmos as a postdoc. And he's still with us today, and he's became the technical director of the program because like he is really, really knowledgeable about computers. We then moved to the University of Bonn in around 2006, and that is where Christoph first entered the scene and like did phenomenal work on the geometry optimizer and early QMMM in ORCA. And although you probably know him best for doing seminal work on the DLP&O stuff, but that was actually after he finished his PhD and stayed for a year as postdoc. That is how golden hands look like then. And it was not until we were in Bonn that it was actually decided to make ORCA a general purpose tool for the general public. So far, it was only a toy that we were using ourselves. So the first 10 years almost were just for internal use. And of course, that makes things quite different. Like once you work on something that's supposed to live for a few decades, the rules of engagement are completely different. And of course, I was 100% oblivious to that when it started. And in 2011, then we moved back to Mülheim to the MPI, and in 2018, then to the MPI for Kohlenforschung, which is on the same campus. And we also founded the FACTS company that has been in operation ever since 2017, and is moving really great. So a very big step for us was the release of ORCA 5. That was in 2021. So when pandemic hit, we were all grounded, and I have to say it was terrible, but it had the positive side effect that people had a lot of time, and I had a lot of time and wasn't traveling and weren't caught up in stupid meetings. And so I started to basically rework the engine, and that led to the Shark integral package that is now driving ORCA. And in 2021, after a year of work, we were at the point where we could release it to the public, where strategic places had been replaced. And and that was a very, very big jump forward. And I think it also doubled the number of ORCA users within a few months. And there were lots and lots of other stuff, especially the COSX implementation was drastically improved. That was Bernardo de Souza and Benjamin Helmich-Pares and Robert Itzhak. And Bernardo made new integration grids and et cetera, et cetera, et cetera. I don't want to read all these features to you because now we're another major step further with ORCA 6, and I'm going to tell you a little bit about what that is. And now let me make just that one remark. So in the beginning, when you start working on such a large project, and you have to consider that ORCA consists of millions of lines of code, and I counted recently, then is the number of source files is in excess of 50,000. Then so it's a huge project. Yeah. And whenever it starts, like you think about something really beautiful and symmetric and well designed and great, and then after 6 or 7 generations of people have worked on it, it usually doesn't look like that anymore. It more looks like this. And that is also what happened to ORCA. And so we did something then after the release of ORCA 5 that I don't think anyone else has ever done. And what we basically did is we put the whole thing in the trash compactor and rewrote the entire infrastructure and the core of the program from scratch. And that is why it took so long from 21 to 24 to release ORCA 6. But it had a massively positive impact. So out of the ruins, so to say, of what used to be the old ORCA that started in 95, emerged ORCA 6. And ORCA 6 is a completely new program that where everything is way more structured and way more streamlined because it was written with the hindsight of more than 20 years of experience. Is it yet perfect? Oh, of course not. There is no such thing as perfect in this world, but it is a major step forward, and I think like it gives us the opportunity to now grow much faster, much better in a much healthier way. Yeah, so no more copy paste orgies that have compromised the cleanliness of the code, and it's a very important question also to think of. The community has to think about what the sustainability of software development is and like how we make sure that our code still run on the computers that we will have in 10 years and 5 years and 20 years. And I think we've made with that step, with these 3 years that we invested in in rewriting the core of the code, I believe we have built a path into the future that is healthy and sustainable. And so let me talk a little bit about the architecture of ORCA 6, because that is also something that changed, right? It was not in the way that is, oh, we need to do this, let's patch it on here, and then we need to do that, let's like squeeze it in there. That is all history now. So the first thing that happened in the old code, like when we went from ORCA 4 to 5, the main new thing that emerged was Shark. And the code looked like this, where we always had branches. And so if Shark is used to this, and if not, do another thing. And there were hundreds and thousands of lines of code like that. In ORCA 6, we've deleted all of that and basically took a completely empty page and started from scratch, and there is no such thing anymore. So the legacy code, yeah, you have to see, I was sitting right here where I'm sitting now, and I did delete years of my life, and of course it hurt. It hurt like hell, but it was it was for a good task, and I think we're really happy and healthy now. So one of the things that we did in the process was to rethink the flow of information through quantum chemical program, and that is in the interest of avoiding redundant code or incoherent code, right? So for example, there are probably 10 or 15 different ways to calculate an optical spectrum in ORCA, and maybe 10 ways to calculate EPR properties. And then what was happening in the old code, that is like the way it was printed, the way it was processed, the way it was handled, was always module specific. And like some people like only took that many of the features of another module when they did the next one, and it was just really difficult to maintain. And I think that's happening in very many of these programs. And that is no longer the case. So the way that ORCA is structured now is that the inner core of it where most of the numerical calculation is happening is Shark. And so Shark is a motor, and Shark doesn't know much about ORCA. Then it's almost nothing. So it's pretty much a computational engine that lives in its own infrastructure. And then what you see as ORCA is a shell that is sitting above Shark. And this shell is basically there to interact with the user and to orchestrate the entire flow of information. And there is an interface between ORCA and Shark that we call the task drivers. And these task drivers, they are the ones that differentiate all of the different approximations and like whether RI is on or how to do exchange correlation integration and whether we need CPCM or relativity. All of these things are handled in the task drivers. That means it's a very clean separation, if you want, so between church and state, where it's clear like the computation is done by Shark. The decision of what is being calculated is done by ORCA, but the ORCA code itself is no longer bothering with details of the approximations and all of these things. That is in a handful of task drivers that are very centralized, so that in these 50,000 lines of files of code, you can actually find it. And above that, now are the workflow tools. So the ones that combine different calculations like a DFT and a couple cluster calculation and this and that, or an extrapolation of something into a workflow. And that is either the compound feature, so it's kind of a scripting language that we have built into ORCA 6, and on the company side, it's the tool called Weasel. These are complementary, but slightly different, but they both have the purpose of creating workflows. And eventually, of course, there are certain graphical user interfaces that people have written or connected to ORCA, and eventually at some point there also will be a genuine ORCA graphical user interface. All right, that is the general structure. And one specific thing that we did that eliminated probably a few million lines of the old code is a completely streamlined way to calculate molecular properties. So as many of you will know that you can express most molecular properties in terms of derivatives of the energy with respect to some parameters like an external electric field or nuclear coordinate, etc. And a first order property is one where there is only a first derivative, and that is usually the first derivative of the Hamiltonian. And that leads to property integrals that are being contracted with an electron or a spin density. And the second order property, like an NMR chemical shift or these things, that is then needs two things. It needs the first and second derivative of the Hamiltonian and then the first derivative of the density matrix. And it really doesn't matter whether this is now DFT or whether it's CAS-SCF or whether it's full CI or whether it's coupled cluster. Everything can be expressed in this way. And we've taken advantage of that in the new infrastructure. So the way it works is that the user interacts with the main program, and then after the initial guess, you do the SCF or CAS-SCF calculation, and then the post-SCF or post-CAS-SCF calculation, and that produces densities, right? Like the non-derivative densities. And they're stored in a central place, a density container, together with the metadata to identify where they were coming from. And then the main program is smart enough to look ahead, so it knows exactly what properties are being calculated and what integrals are needed. And then there is a tool called ORCA propint, and that calculates these property integrals only once. Only once. No matter how through many steps or methods you run, it only calculates this property integral once. And that's a big difference to the old program where like integrals were calculated over and over and over and over again just to be on the safe side. That's one of the worst things that you can do to a program, is like to be on the safe side and then replicate things over and over and over again. So now there's that property container, and after that, it goes into the response modules, and the response modules, they pick up these property integrals as perturbations and then calculate these density derivatives. And that also goes into the density container. And then there is one program only, and that's called ORCA prop. And ORCA prop picks up the property integrals and the density derivatives and calculates molecular properties. And so as soon as you have implemented a new method, or we have implemented a new method in ORCA, and that can calculate a density or a density derivative, the rest is automatic. Everything is automatically available. For example, when we taught the AutoCI generated code how to do derivatives or like properties and densities, we immediately had all properties available that ORCA can calculate. And that is how it will be going into the future. And that's very lean and very clean. And so, for example, if you do an STF calculation, MP2 calculation, a couple cluster calculation, the program will automatically recognize the three densities that are available and will calculate whatever you request, like a dipole moment or quadrupole moment or hyperfine coupling, like for all of those, and you get them next to each other in the output file. So that is, I think, something that's unique to ORCA, and that is a very, very streamlined way of approaching molecular properties. And then I think another thing that was really, really important for ORCA 6 was to rewrite the SEF program. And the SEF program is almost necessarily always the oldest part of each quantum chemistry programs. And over the decades, dozens of people have tried hundreds of things, and that tends to be the messiest part. And so the problem that we had with it, that it was so convoluted that only very, very few people could even work with the old code. And the old code had everything in memory, like the overlap, the S to the minus one half, the S to the plus one half, the kinetic energy, the H core matrix, the several copies of density matrices. And that fired back very badly once you started parallelizing, because we are mostly working with a replicated memory model. And so in rewriting the STF program, I called it lean STF because it was written in a way that no more than two or a maximum of three matrices are in memory at one time, and the rest is put on disk to sleep, so to say. And then using shared memory wherever we can, where there is no conflict, where processes could write in the same memory location, we were able to cut down the memory demands of the STF program dramatically. And that was majorly helpful for the parallelization of the program, that now you can do much, much nicer, much bigger parallel calculations. And you will see a few examples of that in a minute. So here are a few benchmarks, and I think I don't want to talk much longer because we had like these hiccups. But here's an idea of like the kind of evolution of the speed ups of that ORCA has undergone. So when it started, that was ORCA 4, and that is like one of our typical guinea pigs, vancomycin, with a double zeta on the left and triple zeta base set on the right. And so when it started, like up to ORCA 2.4 or so, it was the old cradle integrals that I had written, and I made absolutely every mistake that you can make in programming integrals were in there. And it got dramatically better when we connected to libint after I learned Ed Valeev, a wonderful, great guy. And that was the state of affairs till ORCA 4. Then came Sharp to ORCA 5, and you see a massive increase in performance. And then for ORCA 6, we streamlined it more and more and more. And I think a big part of it is speeding up the chain of spheres exchange that is mostly Bernardo's work. And so we have increased the performance by a very large factor. That's like 20 or 30 or so. That actually is much, much more algorithmic speed increase over computer increase. Yeah. So you see that here. So the algorithmic increase here is in performance is in red, and the CPU speed up, so the way the computers got faster over time, is in blue. And so you see, especially for the triple zeta basis set, the algorithmic speed up is dwarfing the hardware speed up. And I'm showing you that to make the statement that there is still a lot of opportunity for like human creativity and not just hardware gigantomania. Then is we're still outperforming like the hardware. And the best way to improve a program is to think more deeply about and come up with a better algorithm rather than throwing more computers at it. Bernardo is a magician, and he has tirelessly worked on various parts of the algorithm, and one of them was the chain of spheres, which is a very, very big improvement that that he made to that. Really clever, very, very clever work. And that is a big part of the speed increase in ORCA 6. And based on all of these increases, like these speed performance, we can now do enormous calculations with more than 10,000 atoms and probably more than 100,000 basis functions. And so that is great because now you can even in some cases, like skip the QMM or the embedding calculation and do an all-electron calculation on a whole protein, for example. These things are possible. They're still expensive, but they were made possible by like rethinking every aspect of it and streamlining it to the T. And there were also big improvements in the embedding calculations. Part of that was implementing the fast multipole method. That was wonderful postdoc Pauline Collinet and together with Benjamin. And so embedding calculations are easily up to a factor of 4 faster in ORCA 6 than in 5. And now that was also a big one that Bernardo has worked on is geometry optimization. And a geometry optimizer is a work of art. And it's really, really difficult. It's very easy like to write some geometry optimizer and very hard to write a really good one. And the ones that are really good, they have all evolved over many years and have these tiny little tweaks and to improve them. And Bernardo has improved it much better. So the ORCA 6 geometry optimizer is more robust, converges less frequently to structures that have small imaginary modes, and overall also has the number of cycles decreased. Yeah. So that is that. And the last thing that I think I wanted to show you before stopping and giving the word to the other people is the increase in the Hessian performance. So all of the integrals got faster, that's great. But we also found a new way to calculate the Hessian, especially in parallel. And where there is a concept of group parallelization. So we realized that the efficiency of every parallel speedup is decreasing with the number of processors. So we thought it would be cool to go to the point where it's still optimal. So when, say, for 8 processors, you usually still get a speed up of 7.7 or something. And so we divide the available processes into groups of 8 or whatever it is, and then have the perturbations, the nuclear perturbations, assigned to these groups. So we have optimal speed up within each group, and then the groups operate perfectly independently of each other so that the speed up overall is very close to optimal. And so that is why Hessians in ORCA 6 are up to a factor of 4 or more faster than in ORCA 5. And in ORCA 5, they were like at least 3-4 times faster than in ORCA 4. And so I think that's why Hessian calculations, at least I hope that the experience of the people who have tried it here in the audience are a very efficient thing. So there's a lot more, but I think I stop here and we will have lots of opportunity to discuss with you details, inputs, outputs, features, and also problems that you may have and may encounter in using ORCA. I wish all of you a lot of fun for the rest of the day. I will be right here and be happy to answer all of your questions in the chat. Thank you very much.